Here in this section, the goal is to use the Gram Schmidt process to find an orthonormal basis. We start before that with an orthogonal basis. So is it possible, here's the goal, can we take any basis from a vector space? So you recall that if it's a basis in a vector space, that means that those vectors span the vector space and that also these individual vectors are linearly independent. Now, here's the goal for all of that. Basically, we're trying to get to the ideal perfect um, uh, uh, basis outside of the so-called standard basis. And so this idea of a perfect basis is a basis for a local uh, space. A local space basically means that if something is trying to be constructed, if heat or fluid flow is trying to be measured, can we construct a basis for that particular situation? So a local space, um, and so what happens is the Gram-Schmidt process allows us to do that. But to get to the Gram-Schmidt, which has rich applications all over math and also the sciences, we established the idea of orthogonal and orthonormal sets. A set of two or more vectors in a real inner product space is said to be orthogonal if all the pairs of distant vectors in the set are orthogonal. Here, an orthogonal set with each vector that has norm length of 1 is called an orthonormal set. Now we can take an orthogonal vector. As a matter of fact, we can take any vector and we can make that vector a unit vector by dividing it by its norm. Thus, it becomes normalized, but it may not be orthonormal. Ortho here comes from the idea of perpendicularity. So vectors that are orthogonal are basically perpendicular one to another. The angles between them are 90 degrees. So how can you determine that? You recall that if you take the dot product or the inner product of the two vectors, if you get 0, then that implies that the vectors are indeed orthogonal. So the theorem that we start off with is something that we've been really trying to build in the previous chapter as we started with the introduction to vector spaces. Let S be a set that has n vectors. Here we claim that S is orthogonal in that it has vectors in it, the set of non-zero vectors in a product space. Then S is also linearly independent. That's the cool thing about orthogonal vectors. If you have a set of orthogonal vectors, and you get for free linearly independence. So we're basically just establishing the idea that this orthogonal set, 1 is linearly independent. It also spans the vector space. Thus, this particular set S becomes a basis, not just any basis, but an orthogonal basis. So the next theorem, if here S is defined as the same, the set of n vectors, is now on an orthogonal basis. So here these vectors are linearly independent and they also span. We use the idea of spanning to actually define here this vector u. So this vector u here, that if S is indeed a basis, then and S is in V, this very fancy inner product space, and if any vector u and v, then we can write this vector u indeed as a linear combination of the vectors in S. So u becomes a linear combination of these vectors in S. And you remember, to write a linear combination of vectors means that you can write those vectors, or you can write that vector u, say for example, as this linear combination, which basically means that it looks like c sub 1 times v sub 1 plus c sub 2 times v sub 2 plus, and so on, plus c sub n times v sub n. Now, we proved in the previous section that this scalar, this dot product u and v1 divided by the norm of v1 squared, we showed that this guy in the last section is indeed a scalar. So basically, this is c sub 1. So we've been really talking about it since the previous chapter. So now we're trying to get the goal of exactly, where we're trying to get to. So you have the fuel to be able to understand what is here. So u is written as a linear combination of these vectors, which means that these vectors here, v1 to vn, span this big vector space V. So we have linearly independence, and we also have spanning. So we get just the ideal basis in terms of being orthogonal, and then hopefully eventually orthonormal. And the Gram Schmidt process will help us to transform a basis to an orthogonal basis. The part here, part B of the theorem, if S defined the same set of n vectors, is now orthonormal. Orthonormal means that each vector v1 to vn, their norms are 1. So here this is 1, and so on. The norm of v sub n is 1. So that really means that the denominators is just 1, so you don't have them anymore, right? I mean, it's just 1, so it's just the term divided by 1. So we get the same thing up here. So we get the same thing here. It's just that our denominators are equal to 1 if these, there's a big if there, if the vectors are indeed orthonormal, taking that they're first orthogonal, and then each vector has it's a unit vector. So that's pretty cool. But we're going to try to establish that. We do need the projection theorem. We introduced this in the previous lecture. Here, if W is a finite dimensional subspace of an inner product space, you recall that the idea of a subspace is that it satisfies the two major properties of vector addition and scalar multiplication. It's finite. Here, finite dimensional means that you can count the number of vectors within the bases. So we say that is n finite dimensional, so n vectors. So if that be the case, then any vector in u, in V can be expressed exactly one way, and that is that u is equal to w sub 1 plus w sub 2. So here this u has some kind of sum that sums up into the values of the legs of the particular triangle that is formed. Now W sub 1 is in the subspace W, and W sub 2 is in the subspace W perk, or the complement of W, the orthogonal complement. So it's just W2 is just perpendicular to W1. That's all they're saying. Now in algebra, that just works itself out to so in algebra you would work that out, and all you would get is that u squared is equal to w sub 1 squared plus w sub 2 squared. And you would just call that the theorem of Pythagoras. So you get the idea of the norms when you measure the length of u. Here becomes the length of w sub 1 plus the length of w sub 2, and so those norms involve the idea of a square root and then the squaring. So in terms of norms, we have the norm of u squared is equal to the norm of w sub 1 squared plus the norm of w sub 2 squared. So that again looks like Pythagoras. Now u is the sum of w1 and w2. So this looks like the norm of w1 plus w2 is equal to the norm of w1 squared plus the norm of w2 squared. And this is provided that the vectors are indeed orthogonal. Right. So with that in mind, and again, the projection, what we get is that this projection of u onto w gives us w sub 1, or some scalar multiple of w sub 1. Let W be a finite dimensional subspace of an inner product space V. This W here is this space. So if these n vectors is orthogonal, is an orthogonal basis for W, then U is any vector in V. Then we can express here the projection of u onto w within the very same definition that we established earlier. This is it. There's no difference. So what is this u? We're really trying to well define it, that u is actually the projection of u onto w. And so we get that same formula, that it becomes a linear combination of the vectors v1 to vn with their scalars. And then likewise, if each of the vectors here are if they're orthonormal, that means that if each vector, if their norm is equal to 1, then we get the same thing here, but the denominators are 1, right? So we use that idea to try to build what we want, and what we want, let me go back and show you, is we're actually trying to get these values of W sub 2 in some kind of recursive way. Our goal is to find all W sub 2's because they're in the orthogonal complement. So we have that W sub 2 is equal to U minus W sub 1. And the W sub 1 becomes the projection. So see if we can write it out. W sub 2 is equal to U minus the projection of U onto here, this space W. Okay. And we'll do that if you have n vectors in the process according to Gram Schmidt. Just kind of recursive-lize, and I just made that word up probably due to watching too many Jesse Jackson sermons where Jesse just at sometimes he just make up Jesse will just make up a word, right? Sounds good though. We say, yeah, go ahead, Jesse. So anyway, let's see. So every non-zero finite dimensional inner product space has an orthonormal basis. I mean, very fabulous consequence. Please forgive me that I have omitted the theorems, the proofs of such. I believe in your text you will see a standard proof, and so I don't want to be bookish by just giving you the same thing that you could read there to get more insight. Here, the Gram Schmidt process seeks to answer this particular theorem. The Gram Schmidt process says that we can find those orthonormal vectors by giving any basis in a vector space. Well, here's the process. The idea to convert any basis into an orthogonal basis, and then even after that, convert that orthogonal basis to a orthonormal basis. So we start with now here's what we don't know. We don't know these guys, but we are given these guys. Okay. So let V1, this is what I'm looking for. So here we're given this, and then we want to find these guys. So the first thing is to let V1, which is what I'm looking for, let that be the first vector. Let that be the first vector in the given basis. And then the process of finding V sub 2 would be, again, it's a U minus the projection. See that? So this is U sub 2, which I'm given that minus the projection basically of U sub 2 on V sub 1. And so that becomes just the dot product in the numerator, and then divided by this norm of V sub 1 squared times V sub 1. If there are three vectors, then we repeat this process again. Do you see the recursion? So V sub 3 is equal now to U sub 3, which comes from here, minus so this is the dot product of U sub 3 V sub 1 divided by V sub 1, the norm of that squared, times V sub 1, minus the dot product of U sub 3 and V sub 2 divided by the norm of V sub 2 squared times V sub 2. You repeat that based on how many n's that you have, and typically for us it's only going to be three vectors. 2 vectors for the 2 space, 3 vectors for the for R3. Now, to the question of finding an orthonormal set, we take each vector that we get, that we find, which are orthogonal, v1 to vn, found from above, and divide each vector by its associated norm to produce the orthonormal set. And so, suppose let the set here be the orthonormal set. This is indeed for R3. Then we can define Q sub 1 as such, and then likewise. And so there, that forces the vectors v sub 1, v2, v3. And if you have n all the way to v sub n, it forces these guys to be written as orthonormal by dividing those vectors by their respective norms. So with that said, without further ado, let's look at this problem. So we're going to convert these vectors in this basis to a orthogonal basis. So we first say let v sub 1, here this is u sub 1, u sub 2, and u sub 3. So let v sub 1 equal to u sub 1. So this is 2, 1, negative 2. And then so that's given, so that's easy. So let v sub 2 equal to u sub 2 minus that projection of u sub 2 on the previous vector, v sub 1. So this is u sub 2 minus the inner product of u sub 2 with v sub 1 all over the norm of v sub 1 squared times v sub 1. So let's work that one out. So v sub 2 is equal to u sub 1, u sub 2, so let me write that. So u sub 2 is 1 comma 2 comma 2 minus here this dot product of u sub 2, 1, 2, 2, with v sub 1, the previous one, 2, 1, negative 2, all over the norm of v sub 1, which we got that to be 2, 1, negative 2 to be squared. And that's, the denominator is just the inner product of v sub 1, and then times v sub 1, 2, 1, negative 2. So this v sub 2 is equal to 1 comma 2 comma 2 minus, take the dot product, we get 2 plus 2, that gives us 4 minus 4, so we get 0. So that guy goes out. So 0 times anything is just 0. So this is just 1 comma 2 comma 2. So, and if you think about it, I mean, it's kind of funny where they give us this basis, and it's unfortunate that the basis is already rigged, because if you look at the first two vectors, you take their dot products, they are already orthogonal, right? So does that happen with respect to that third vector with u1 and u2? Then you have to determine that by the dot products, right? So v sub 3 is equal to u sub 3 minus the projection of u sub 3 on v sub 1 minus the projection of u sub 3 onto v sub 2. So u sub 3, that's given to be 2 comma negative 2 comma 1, and then that's minus the dot product of u sub 3 dot product with v sub 1, and v sub 1 is 2 1 negative 2 all over the, let me write this down here, I forgot that's pretty long. So it's all over the norm of v sub 1 squared times v sub 1. Then now minus the projection of u sub 3 onto v sub 2. So u sub 3, take the dot product, this is 2 negative 2 and 1 dot product with v sub 2, got that to be 1 2 2 all over the norm of v sub 2 to be squared times v sub 2, 1 2 2. So now it's just a matter of just working that out. So here v sub 3, this is 2 negative 2 and 1 minus, do the dot product here, so this is 4 minus 2, which is 2 minus 2, so that guy goes out, and that's 0. Looks like they've given us an orthogonal set from the beginning. So here we get 0 there, then minus, and I think we did this above in v sub 2, we get 0 here as well. This is 2 minus 2, which is minus 2 minus 4, plus 2, which is also 0. So this guy is 2 negative 2 1. Now again, this problem is rigged where b is already orthogonal. So this typically, doesn't happen. I mean, why would you even do this? I mean, you're giving me something that's already been done. So I'm going to work the next problem, another problem, to show you that this is really not supposed to happen. But I know what WebAssign is doing. They're trying to give you basically, easy stuff, because this process with these problems, you have a lot of radicals and a lot of simplification and that kind of thing. So let me go to the next page and make sure I have this information here. So u sub 1 is 2. It is 2 negative 2 and 1. No, that's 2 1 and negative 2. And then v sub 1 is that. V sub 2 we got to be 1 2 and 2, and then basically it's just the original basis. V sub 3 is the 2 v sub 3 is the 2 negative 2 and 1. I was trying to see that on my paper. I guess I didn't write it down. Okay, I see it. So we have v sub 1, and that is 2 1 negative 2. V sub 2 is 1 2 and 2, and then v sub 3 is 2 negative 2 and 1. So from here I'm going to use the process to find the orthonormal vectors. So I need the norms of each of these. So this is 4 plus 1 plus 4. So it gives us 3. For v sub 2, we get the square root of 1 plus 4 plus 4. There we get 3. And the norm of v sub 3 is the same. Again, these problems are definitely rigged, right? So q sub 1 is the v sub 1 over the norm of v sub 1. So this is that 2, 1, negative 2 over 3. So we get 2/3, 1/3, and negative 2/3. Q sub 2 is that v sub 2 over the norm of v sub 2. There's 1, 2, and 2 divided by 3. So it gives us 1/3, 2/3, and 2/3. Q sub 3 is the v sub 3 divided by the norm of v sub 3. It's 2, negative 2, 1 all over the norm of v sub 3, which is 3. Two-thirds, negative 2/3, and 1/3. And you can see them there. What they call theirs U1, U2, and U3. Doesn't matter about what letter you use. Dr. Wallace Maryland used to say at Alabama State, you can call letters, you can change them, and that's fine. They won't get upset with you like people, right? Matter of fact, he would say letters are dummies, not people. So since letters are dummies, you can change the letter and say, okay, I said it was Q, but let's say it's R, or let's say it's V. You had better check these guys as well. So check Q1 dot with Q2. Make sure you get 0. So here we get, that's 2/3 plus 2/3 minus 4/3. So that's 0. And you check all the combinations. Q1 dot with Q2. So that's 2/3 times 2/3 is 4/3 minus 2/3 minus 2/3. We get 0. That's Q3. Excuse me. Check Q2 and Q3. So this is 2/3 minus 4/3 plus 2/3. So you remember that the vectors are 1 orthogonal if the dot product is equal to 0. And I think that satisfies the combinations. Oh boy, my combinatoric skills lack sometimes in things taking R at a time, right? So I think that does it. Yeah, we do. Q1 and Q2, Q1 and Q3, and then Q2 and Q3. And the since this is not permutation, where the order is not significant, so Q1, Q2, Q2, Q3 is commutative, so we get the same thing. So that's cool. Now I'm gonna do one more because I think this problem was a dud. It was dead on arrival because the vectors that they give you were already I believe orthogonal. I mean, so there was nothing to do there. I was like, dang, U1 dot with U2. Look at that. That's 2 plus 2 minus 4, 0. U1 dot with U3, 4 minus 2 minus 2, 0. U1, U2 and U3, excuse me. And that's probably a good thing to check. Check in the beginning. If they're all orthogonal, then I mean you're basically really done. You just do the orthonormal. So it's 2 minus 4 plus 2. Well, I'll be dang. I wanted to say like Doc Holliday when he was dying, but he didn't say dang. I don't know if they even had the word dang back then. You know, Eddie Murphy said we couldn't even say dang when we was growing up. Mama said it sounded too much like, you know. All right, let's look at this guy right here, and then I'm going to get out your way. This what my friend. He wasn't little. He was older than me. I was probably like in the third, fourth grade, and Trey was probably in the fifth, sixth grade. And he was a little bit older than us. And a lot of the guys up in Indianapolis when I grew up back in the '70s, late '70s, early '80s. We used to play out there in the park and at the tennis court. And had skateboards and stuff. And Trey this guy was very smart, man. When we moved up there from Alabama, he was taking styrofoam and making motor cars and motor boats, and he taught me how to do that, and just a very fascinating guy. And so, I was always inquisitive when it came to electronics and science and mathematics. So um, it was weird because when I was in school as a boy, my mind was not there because it was so boring. But when I get home and get with Trey, we'd take a walkie-talkie apart and try to extend its area so that we could talk on walkie-talkies from our apartments and stuff. But he'll be telling me something, and he say, "Hey man, I got one more thing before I let you go." And and I was a kid, I was thinking, you're not holding me down where you're saying, let me go. I can leave when I want to leave, but you go ahead and tell me what you got to tell me, Trey. Yeah, he's a cool guy. So anyway, let's get here. A matter of fact, he called me. This has been like it was like 35 years later. He figured out how to get my number, I guess, on Facebook or whatever, and he gave me a call and told me what he was doing. I think he's in Atlanta with his family. He's, I think, a coach of I think the track team for the military, I think for the army, I believe. I forget which branch, and they travel all over the country with his team. And I was like, man, that's just fascinating. We moved back to Alabama, so I kind of lost touch with a lot of those guys. But anyway, um, so one more problem before I let you go. How about that? Yeah. We need black. Let So again, this is U sub 1, U sub 2. This is what I'm calling it, right? So let V sub 1 equal to U sub 1, and that's 5, negative 12, and 0. And then let V sub 2 equal to U sub 2 minus, just going to go ahead and just put it here. This is the inner product of U sub 2 and V sub 1 all over the norm of V sub 1 squared times V sub 1. So U sub 2 is at 5, 1, 0 minus the dot product of 5, 1, 0 with V sub 1, which is 5, negative 12, and 0, divided by the norm of V sub 1 to be squared. And so this is the norm of V sub 1. That's the 5, negative 12, 0 to be squared, then times V sub 1. So v sub 2, we get 5, 1, 0, minus, take the dot product, that gives us the 25 minus 12, so we get 13, then, plus 0, all over here, that norm of 5, negative 12, 0 is the square root. Come on back up. So it's 25 plus 144. So this is the square root of 169. And so that gives us 13. But we're squaring that, so that's just 169. This is times 5, negative 12, and 0. So we get 5, 1, 0 minus, that's 1 over 13, times 5, negative 12, and 0. So v sub 2 is, so this is 5, 1, 0 minus 5 over 13, negative 12 over 13, and 0. Right? So, and see, you work that out, and I worked that out. It's funny when you have everything everywhere. So we get 5 minus 5 over 13, so that gives us 60 over 13. And then 1 minus a minus 12 over 13 is 1 plus 12 over 13. So that gives us 25 over 13 and 0. Now v sub 3 is the u sub 3 minus the inner product of u sub 3 and v sub 1 over the norm of v sub 1 squared times v sub 1 minus the inner product of u sub 3 and v sub 2 over the norm of v sub 2 squared times v sub 2. Okay, so v sub 3, the u sub 3 is that 0, 0, 4 minus the dot product of 0, 0, 4 with v sub 1, which is the 5, negative 12, and 0, all over the norm of v sub 1 squared, and we got that to be 169, and that's times v sub 1, 5, negative 12, and 0, and then minus u sub 3 dot with v sub 2, and v sub 2, we just got that guy, and that's the 60 over 13, 25 over 13, and 0, all over its norm. So I'm not going to find it because this dot product is going to give me 0 anyway. So the norm of 60 over 13, 25 over 13, and 0 times v sub 2. Alright. So let's look at this. You take the dot product here and you take the dot product over there. So the dot product for the first one is going to be 0 times 5, 0, 0 times negative 12 is 0, 4 times 0, 0. So this guy is 0. So the whole thing right there is 0. Then over here, 0 times the 60 over 13 is 0. 0 times 25 over 13 is 0. 4 times 0. This whole thing right here is 0. So all you have left is just v sub 3 is equal to u sub 3. So it's 0, 0, 4. Okay. So let me see where I wrote that so I can change the page. Okay, I think I got it. So we found v sub 1. Let's get the black. So the v sub 1 is 5, negative 12, and 0. V sub 2, we found, where did I put it? So is that 60 over 13, 25 over 13? I have to go back and check my sign. Then v sub 3 is that 0, 0, 4. So v sub 2, okay, so it's all positive, 60, 25, and 0. And the v sub 1, we got it. So now we find the orthonormal vector. So this is 5, negative 12, 0 divided by, remember we found that one to be, it was the square root of 169, so that just gives us 13 downstairs. So this is 5 over 13, negative 12 over 13, and 0. And for this next one, just take that norm of v sub 2 first. Let's find it. So this is the 60 over 13 to be squared plus 25 over 13 to be squared plus 0. And in that guy, notice that for the denominators are the same, 13 to be squared. So this just becomes 1 over 13 on the outside times the square root of that 60 to be squared plus 25 to be squared. So that gives us, that inside there is 4,225, and you take the square root of that, you get 65. So this is just 65 over 13. And if you don't like my simplification, then you just do it the way you want to do it, you know, and I'm cool with that. So where did he get the 13 on the outside? You just do it your way, and we're all satisfied. Right. So q sub 2 is v sub 2 over the norm of v sub 2. So v sub 2 is that 60 over 13, 25 over 13, and 0. That's all over the 65 over 13. So when we divide, the 13 in the bottom goes upstairs, 65 goes on the bottom. So that's the 13s cancel out. So we have left 60 over 65, 25 over 65, and 0. And then we simplify that, and the 60 over 65, just a common factor of a 5, so this is just 12 over 13, 5 over 13, and 0. Okay. So q sub 3 is v sub 3 divided by the norm of v sub 3. So we get v sub 3 is 0, 0, 4 divided by, you take the norm of that, you just get 4, right? So this is just 0, 0, 1. And I think we have them. Q sub 1 we get here. That's the same thing there. And then Q sub 2 here. And that's the same thing there. And then Q sub 3 is here. And that's the same thing there. And as my friend Trey used to say, um, um, I'm going to let you go. So you all take care.